So much, Bronwyn. That was a wonderful introduction there. And yeah, so I'm at Towson now, and I've been here for the past 10 years. And I'm very excited because the next frontier in astronomy is about to open up. And it's all thanks to our folks down the road who are studying the using the James Webb Space Telescope. And so I'm going to give you a talk today, try to do my little share here, discussing a little bit about where did telescopes come from? When did we start using them? And believe it or not, that's not a very clear thing. And then how did we modify telescopes to be of the maximum use that we can possibly have? And then at what point did we start sticking them in space, and what was the point of all of that? So I'm going to try and talk to you about all of that today, and I hope that you'll enjoy this. So here is a little picture, an engraving that was appeared in a book, and it was referred to as the Dutch telescope, and it was in a book called the Emblemata of Zinnewerk. And this was the engraver who published this picture in the book. His name was Adrian van der Ven, and he published this back in Middelburg in Netherlands in 1624. And the reason why this is interesting is that the bookshop, the book publishing company that he worked for, and where he decided to draw this picture for the book, they just happened to be down the road from this spectacle maker and optician, and his name was Hans Lippershey. And notice there's no S in this. It looks like the name Lippershey got turned into Lippershey at some point when it got translated into English. And he was a spectacle maker and an expert on optics. And in the year 1608, so that's just a few years before this engraving was made here with the telescope, he tried to patent what he called a telescope. And his plan was to try and make a handsome profit off of that. And so he filed this patent with the government of the Netherlands. And it turns out that his attempt failed. And the reason it failed was that this whole idea of telescopes, of putting two lenses together and looking at things, actually was kind of in the air. And if you remember that episode of Seinfeld where Elaine, she invents a certain kind of like a donut shop, and this other guy gets mad at her and says, you stole my idea. And she said, these ideas, they're in the air, they're in the air. Well, it was in the air here at this time. And so he was denied a patent from it. But his claim for the patent that he was trying to put in was he had made an instrument that was for seeing things far away as if they were nearby. That was his selling point there. And so although he's the name that is often associated with it, there were a number of other people at this time who were doing very similar things. And so the person who's most important who picked this up was Galileo Galilei. And here's a picture showing what he would have looked like when he was young. And he created a telescope using this design that Lippershey came up with. And this is his actual telescope in the museum in Florence. And this is the main scope here. And then this, I believe, is the finder scope that goes with it. And he used this very extensively. And it doesn't look like much here, but it actually revolutionized astronomy. And so he improved on Lippershey's design only 2 years after Lippershey tried to file for a patent on this. So this was indeed in the air. And the thing that made Galileo different was that, well, first he really improved the design of the telescopes, the optics, the grinding of the lenses and the setup. And he was also the first person to actually turn it, that we know of, to the sky and really record his observations. Everyone had been using a telescope up till then to look at ships far away or trying to spot enemies coming to your tower so you could drop bombs on them. And so they were using it for things other than astronomy. And so Galileo was the one who used this. And my God, this is one of the reasons why, the main reason why in the poll he won as being the greatest astronomer, because he made some really incredible discoveries. So first off, let me just point out that the first telescopes here, they used only lenses. And so here's a picture of a lens observed from the side. And we like to say that when we put these into telescopes, we say the big lens, we call that the aperture, and the diameter of that is what we call the diameter of your telescope. And the idea is that if light rays from a faraway source, like a star, for example, come into your telescope, this will bend light. It's called refraction, and it brings them together, the rays together at one point, and this is where you form an image of what you're looking at. So this is how you would burn, for example, a spot onto a sheet of paper in the summertime. You form an image of the sun on a spot. Well, you can do this with stars as well. And if you come in here and you measure how far away from the lens these rays come together, that length over there, that's called the focal length of the lens. And this is an important thing that people measured with telescopes. Now, the question is, why in the world do we need two lenses for a telescope? Why isn't just one enough? And I'm going to try and explain to you why that is. The reason is that if you have a lens here, and then here's the focal length of a lens, these 2 points show where rays come together. If you imagine you're looking at a galaxy very far away with this, and imagine the rays from the galaxy come into the lens and they come together like that, they're going to form a very bright image of this galaxy. The reason why it's so bright is that this lens is able to gather all these rays that would have missed our eyes, instead went into this lens and were brought together and focused into one point. And so you form this beautiful, very bright image of the galaxy. But there's only one problem. This image is still tiny. And so it's not really good. If you want to look at it, you're not going to see much detail. So the revolutionary idea was we bring in another lens like this. And this second lens has its own little focal length over there. And we line up these focal lengths so they almost land on top of each other. And then the idea is that this galaxy over here, the light that comes from this galaxy, these rays, once they cross and make that image, the rays then continue on. Let me go to here. The rays continue on like this, and they hit the second lens, and they then spread apart. And when they do that, they spread apart in just such a way that if you stick your eye over here where these rays are coming in, your eye tracks these rays back, and it thinks, oh, there's an image of this galaxy in front of my telescope, and it's really huge and very, very bright. And so this second image over here is the one where you took the bright object and you magnified it into something really big. And so as you can see, a telescope has a couple of very important functions. And so the idea is that telescopes do these things. One thing is they make them look bigger. And so telescopes are almost like a magnifying glass for the stars. And this is, unfortunately, this is the main thing people seem to be most preoccupied with when they go to a store and want to buy a telescope. They say, how do I make that thing look bigger? But you know what? That thing, it doesn't matter how big you make it. If you spread it out so much that it gets very faint, it's not any good. So you also have to make it look brighter. And so that's the function of the aperture of the telescope. And it turns out that the bigger the lens, the larger the lens is, the more light you can take in and the brighter your object can be. And then finally, and this is another thing people don't think about very much though, is that telescopes allow you to make out a lot of detail. So if you can magnify a galaxy to a very large image, you can make out all the details of the spiral arms and the dust lanes and all the little parts of that. That gives you a lot of information. So these are all things that a telescope really is supposed to do. And this is why they had to use two lenses for that. So Galileo went to town with his telescope, and one of the things, and this is an image from one of his notebooks actually that he made, very intricate drawing, he noticed that Venus seemed to go through phases, and nobody had ever noticed that before because no one could see Venus up so close. And so here's an image of Venus that he took, that he drew from his telescope when it was just a crescent, and here's where it looks like it's getting more and more full. And you'll notice that as it gets full, it's looking smaller and smaller. And so he noticed this, and it turns out, and this is what led him to say, you know what, I think Copernicus's model of the Earth being the center of everything is wrong. What it led him to believe is that, no, if we're standing here on the Earth and we're looking and the sun is over here, that Venus had to be orbiting around the sun. And so only if it's orbiting the sun can you account for all of these phases that we're seeing in his pictures. It would not work if Venus were going around the Earth. And so so this was a very important realization, and it was one of the main hammer blows against the Earth-centric view of the heavens. So a very important development for him. Here's another thing that Galileo found. He looked at Jupiter's moons. So the planet Jupiter, many of us notice very bright out there in the sky, but again, you can't see any detail. Well, when he turned his telescope to it, and his telescope did not have, like, it wasn't the highest quality object, but he was able to notice that, wait, each day, and these are the days he's ticking off, he noticed that it seemed like the moons were on a different side of Jupiter every night. And he noticed to his astonishment that there are bodies orbiting Jupiter. And that really like blew his mind, because he said, well, look, we're seeing another object in the solar system that has things going around it. And so that doesn't make the Earth so unique anymore. Maybe that's just further evidence that maybe everything doesn't go around. And so here is a modern day picture of what he was drawing. This is a picture taken through a large amateur telescope of the planet Jupiter and these moons over here. And we are kind of fortunate that the moons are named these now, because originally he named them after family members of the Medici clan in Italy. And later on, scientists thought that was kind of in bad taste, and so they named them instead after these other mythological names. And so we can thank them to that day. So now, what is one of the problems? So what led people to continue to tinker with telescope design? Well, one of the problems is there's this little thing called chromatic aberration. Chromatic is Greek for color, and aberration means when the image looks messed up. And so this chromatic aberration means when your image looks messed up and colorful. And so the idea is that if you have these two lenses here with a telescope, if you send in white light from a star, say, into the lens, there's this problem where light is made out of all the colors of the rainbow. And the red part of that light, if you focus it, it makes an image that looks like this. But if now you look at what happens to the green component of the light, it will cross a little bit closer to the main lens. And if you look at what happens to the blue light, it comes together even closer to the main lens. And so you have, in effect, 3 focal points, one for every color. And so you end up with this superposition of images that looks really messed up. And you have this blurry image with color around it. And so here's an example of what this might look like. So here's an image that was taken with the moon, with chromatic aberration still there. And you can see these blue and red halos around it, and it's blurry. It looks really awful. And they have to, there are corrective lenses that you can put in here that will fix this, but this adds to the cost of a telescope. And so chromatic aberration is a big problem with these kinds of lens-based telescopes. Okay. So one of the problems, other problems with the refractor. So here's an example of a really fantastic refractor at Swarthmore Observatory. This is Swarthmore College. This is Sproul Observatory, the 24-inch refracting telescope, and you can see a very long tube, and the lenses, become very large. But the problem is that correcting for the chromatic aberration gets harder and harder. And if you want to get a more and more powerful telescope, your lenses have to get bigger and heavier, and your tubes have to get longer. And so this is a problem because your tubes start to sag under the weight of these bigger and bigger lenses. And so this is expensive, and it's not something that you can really run away with. These telescopes only get so big before they become unwieldy. And so it is these kinds of limitations that led none other than this fellow Isaac Newton here to come along and say, hey, how about if instead of using lenses, what if we use mirrors instead? And so this is an actual telescope from the collection of Newton that he created that features a mirror at the back of this long tube, and there's no lens out here front like that. And so he tried to get around chromatic aberration by just not using lenses at all. And so the idea is to use mirrors. And from then on, this has become really the preferred way that professional astronomers do their work. And so and actually I wouldn't say from then on, rather this limitation, this new design is what people decided to go with when they wanted to make telescopes larger in the 20th century. So, so here's an example of what this looks like. So if you look at a cross section of Newton's scope, so you go back to this, you take this here and you cut it in half. Here's where your mirror is located. So your light rays come in from the faraway source and they bounce off the mirror. And because the mirror is curved, the light rays then come together like this in front of the mirror right here. And so you can talk about a focal length for these mirrors too, just like you could for a lens. It's this long distance in front of the mirror where the rays come together. And so the primary mirror then, because it's at the back end of the telescope, it no longer has problems with sagging tubes or being too big or whatever. You can make the sucker as big as you want, this primary mirror. And so this is why the reflecting telescope became the main thing that method that people are using now. And you can talk about an aperture there too, like how big is that? How much light does it collect? The place where the rays come together is what we call a prime focus in these telescopes. So, so it turns out there are 3 main telescope types that are out there. There are 3 main telescope types that are out there. One of them is what I just showed you here before, but then Isaac Newton's version of this was to take these rays where they come together. Obviously, you can't stick your head into the tube of the telescope and try to look at the image because it will block the light. So he said, well, how about if I take this light and I stick a mirror here and I reflect that light up through a hole in the side of a telescope, and then you can stick your eye in over here at the top. And so this Newtonian design was what he favored, and he thought it would made it easy to see things. There's another design over here that kind of takes this idea. And now instead of sending the light rays, reflecting them up through the side, it reflects them back to the back end of the telescope, so it comes out of the back. This is called the Cassegrain design. It's named after a French optical person, and optical scientist and a telescope maker himself. And believe it or not, this is the main design that you often see with today's telescopes, the more sophisticated kinds that amateurs use. You can see here, there's the tube, the mirror is in the back, and right over here, this is that reflecting mirror, and it sends the light through the back end, and you can see where the eyepiece is over there. The light goes out the back. So this design, the Cassegrain design, believe it or not, is also the same design that's used for the James Webb Space Telescope. So just to point out here, I think you can all pretty obviously see that this is the main mirror of James Webb. And you'll also notice it doesn't look like a nice circle. It looks like a bunch of little honeycombs stuck together. And they have to be kept in a perfect shape, so that if you look from the side, it looks like a perfect, kind of like a parabolic shape, so that when light comes in from far away and bounces off, it then comes here and hits this mirror and then goes through the hole in here and gets channeled down into the instruments that are down below the main part of the telescope like that. And so this kind of a design is the preferred design that many telescopes use nowadays. So this is where things ended up after a few centuries of refinement. So, oh, and by the way, James Webb, I guess maybe everybody knows this, but James Webb is the largest space telescope ever just deployed, and it's probably the most complicated piece of technical equipment we've ever created. And part of the difficulty is that in designing this was that they knew what they wanted to do, but they had to invent a technology as they went along. And so to have to invent a technology and build it and test it and do it all at the same time is hugely difficult and time consuming. And that's one of the reasons why it took so long to develop the James Webb Space Telescope. Now, I want to get technical with you. So let's talk here. In astronomy, we measure angular sizes. And what do I mean? So if you have, this is a circle, and a circle, if you go all the way around, that's 360 degrees. And if you look at objects in the sky, like the moon, or you look at a galaxy, or you look at the sun, you can measure the angular size, how many degrees in the sky something is, but you don't actually know physically how big it is unless you know how far away it is. And so one of the ways that we try to measure angles is we take these degrees and we chop them up into little pieces. So here's a protractor. And if you take this here and you chop up each one of these degrees, chop it up into 60 pieces, you call those arc minutes. And if you take each of these little arc minutes, chop it up into 60 pieces, that's called arc seconds. And so 1 degree is 3,600 arc seconds. And so each one of these apostrophes you see here has a relevance. So 1 apostrophe is arc minutes, 2 is arc seconds. So an arc second is really tiny. We're talking about 1/3600th of a degree. And to give you a sense of how big that is, or how small that is, the moon on the sky is about 1,800 arc seconds across the diameter of the moon, the projected size. So an arc second is a really tiny angular size. And so now let's try and take this and talk about this in a physical way. So if you take a soccer ball that we know and love, and imagine now that you look at the soccer ball and you put it 45 kilometers away, that's very, very far, right? That's like way in the next city. Then that soccer ball, the angular size of that as measured by you will be about an arc second. And so that's how tiny that is. So that soccer ball. And so the angular resolution is something that you can define. Angular resolution is what is the smallest angular size of something that you can discern and make out. And it turns out that, I'm simplifying over here, it turns out it's approximately equal to the ratio of the wavelength where you're observing. If you're observing through a filter and you're looking at 500 nanometer light, then that's what you plug in. It's the wavelength you're observing at divided by how big the aperture size of a telescope is. And this is important because this ratio over here tells you what is the smallest angular thing that you can make out with your eye. And this is also this description of resolution. This is called the diffraction limit. This is a nice technical term they use in optical astronomy. It means what is the smallest discernible thing that you can make out given the limitations of the wave-like properties of light. That's what that is. And so the basic picture here is that the larger your telescope aperture is, the bigger this gets, the smaller the angular size that you can resolve. So you want this angular resolution number, you want it to be very small. And that way, virtually everything you look at is going to be bigger than that. And so you're going to be able to make out what you're seeing. And the human eye has a resolution of about 20 arc seconds or so, given, if we look at our eyes and think of them as being like a telescope, it's an aperture, they're fully dilated pupil like that. Our resolution is about 20 arc seconds. And so since the soccer ball is only 1 arc second in size, that means we would not be able to see any detail on it. We would not be able to make out any of the patches on it. It would look like just an unresolvable dot way in the distance. And so we would not be able to resolve that. And so size does matter when it comes to telescopes. And so this, by the way, explains, folks, why do astronomers keep trying to make telescopes bigger and bigger and bigger? It's because of this denominator here, telescope diameter. The bigger that gets, the smaller, the smallest angular size that you can make out. So that's the whole point. That's the name of the game. That's why we're doing that. And so here's just an example. If you use a 1 meter across telescope and you're observing something at 500 nanometers, that's visible light. Here, the minimum resolvable angle is an arc second for something, but then those same 2 stars, the minimum resolvable angle is less than an arc second, and so you're able to tell the 2 stars apart. And that's all happening because you're looking at it with a bigger scope. So you can look at the same 2 stars between these 2 scopes, and in one of them they look like a blob, and in the other one they look like 2 sources. And the holy grail is you want to make out sources, you want to see detail. So so this is why you want telescopes to be big. You don't want them to be small. You want to be able to make out that detail. So here's another thing that comes into play when you look at with a telescope. When you look out into the night sky, atmospheric turbulence of the Earth's atmosphere has a big impact on the light that you see, because these straight lines here, these are like wave fronts, the light coming from your star, and it wants to enter your telescope. But as it's going through the air, it encounters these pockets of air, some of them that are warmer and some are cooler, and air is moving around and turbulent. And that actually, it messes up the wave fronts of the light. And so by the time the light gets to your telescope and gets imaged, the images of all these are blurred. And that's because all that light that came in, it got smeared out by all this jiggling in the atmosphere. And so this is referred to as atmospheric seeing, is what they call this in astronomy. Seeing is how smudged out your stars are as observed with your telescope. And this is the same thing that causes twinkling of stars in the night sky. It's atmospheric turbulence. And guess what? There's no way to get around that. The only way you can get around that is to go above the atmosphere, and that's when the problem goes away. So here's a picture that just shows how transparent the atmosphere is, or how opaque it is. And you can see that the rainbow here, this shows the whole electromagnetic spectrum, the visible band that you and I see every day. The atmosphere is pretty transparent to it, but it's not totally transparent. There's a little bit of opacity there. But if you take Hubble and stick it out above the Earth's atmosphere, you get rid of that problem. There's no more twinkling, no nothing. And even more important, the James Webb Space Telescope here, it observes in the wave band that starts in the red part of the optical and goes all the way out to the mid-infrared like that. And so it is able to observe at wavelengths that are even longer. And it doesn't have to worry about all these little spikes in opaqueness of the atmosphere and twinkling and all of that either. So both Hubble and James Webb are going to get around that twinkling of the atmosphere. That is why they are in space, because you're going to get your maximum resolution possible. Okay, so here's just an example of what images look like if you take something from the ground. This is a very large telescope. This is a Gemini North telescope. It's one of the biggest ones we have. The diameter of this mirror is approaching 30 feet. And it has the resolution, the best resolution it can get with atmospheric distortion is about 0.2 arc seconds. So here's an image of this beautiful nebula taken with that. Here's the same thing taken with Hubble, and it has a resolution of 0.05 arc seconds. So like 4 times better spatial resolution. And you can see how sharp and fine of detail it is that you can make out with all of this. So this is all being done with visible light. Now, let me just give you a rundown here of what are the pros and cons of an observatory on the ground versus what's up there in space. Well, if you look at angular resolution, which everybody wants to have, on the ground, you can't reach your maximum resolution because of smearing, the atmospheric turbulence. So that limits what you have. In space, there's no atmosphere, no problem. You can get to your maximum diffraction limit resolution. Cost is another factor. So here, if you look at cost, on the ground, telescopes they're easier and they're cheaper to build because you can reach them and you can go service them and change them. For space, well, once you stick that thing in orbit, it's very, very difficult to fix it and change it because it's already in orbit. Maintenance, if something breaks, what happens? Well, on the ground, it's accessible and it's upgradable. You can do whatever you need to there. But usually, I say usually, telescopes cannot be serviced once they are launched. And of course, one glaring counterexample is Hubble. There were 4 servicing missions that went up in the shuttle to fix and to adjust Hubble. And that was because it's in a low Earth orbit. But most telescopes, you can't do that. Aperture size. So on the ground, you want to make your aperture as large as possible. But guess what? When you want to launch in space, it's actually limited by the launch vehicle. It's limited by how wide the rocket is. You can't make a rocket that's like 100 feet wide. You're never going to get that thing into space. So although you have all this wonderful spatial resolution up in space, you are limited by your launch vehicle, how big of a thing you can put into it. And then wavelength, like I showed you a moment ago, on the ground, you can't see all wavelengths, only the visible and some IR and some radio. But in space, you have the whole electromagnetic spectrum. So there are pros and cons associated with the ground versus space. On the ground, it's easier to maintain stuff and less expensive, but in space, you really get your maximum bang for your buck. So you have to do maximum risk and maximum expense to really get at the best stuff. And so this is why we are building Hubble and why we are building Webb. So let me just show you a picture here. So what's so special about JW? So here are 2 different views of the same part of the galactic plane. So this here is a picture that was taken in a very rich area of the Milky Way galaxy where there's lots of stars. And here are a couple of star clusters, and here's a star. This was taken on the ground in the visible band. Well, now if you want to observe that very same field in the infrared, this is what it looks like. And you see how it looks a lot less interesting and a lot less rich than this one does, even though they're the same field. You'll notice here that there are many, 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 many stars crowded together. Over here, you don't see. Most of them are smushed together because you don't have the resolution. And the reason is that when I told you that smallest angle that you can make out, it depends on the ratio of wavelength you're observing at divided by the size of a telescope. If that wavelength is long, like infrared, you're not going to have very good resolution. It's going to be very hard to get anything good. And so from the ground, trying to observe anything in the infrared, you're very severely limited no matter how big your scope is. So just to point out to you here, so here, this is a simulation that was done over here of what stars would look like. This is not a literal picture. This is just a theoretical thing showing if you had a lot of stars placed close together, what it would look like if you look with Hubble. In the near infrared, Hubble has its best resolvable detail is 0.05 arc seconds. And guess what? James Webb is going to get that same kind of resolution, but it's going to get it through the full band of the infrared, and it's going to be able to make out details. It's going to be able to separate out stars from one another in a way that you could never do from the ground. That would have been impossible. And so this is where James Webb, being above the atmosphere and having this fantastic optics, is able to really deliver on spatial resolution. And it's one of the biggest things that we want with telescopes. So here's just a comparison, Hubble versus James Webb. Here is Hubble here, and this is a 2.4 diameter mirror. Here's the size of a person. James Webb is going to be much bigger, 6.5 meters. And you notice there's a hole in the middle, which is where the light goes in because you have a Cassegrain type design. This is one of the mirror segments, and you notice that they're wearing these clean room suits on here, and they don't want to get any specks of dust or anything on this thing because any bit of speck of dust is going to mess up any reflections of light off of that, and it's going to mess up your imagery. So you want to stay very clean when you're bringing these all these mirror segments together. So now where's James Webb going to go? So here's the sun, and here's the Earth, and the Earth follows this orbit around the sun. And the Earth is 150 million kilometers away from the sun, and the moon is following it in an orbit like that. And so the idea is they are going to launch James Webb from the Earth, and in a period of about a month, it's going to travel all the way out to this point called L2. This is about 1.5 million kilometers from the Earth. And notice that it's on the far side of the Earth from where the sun is, like that. So it's sitting here, and the Earth and the sun are on the same side. Now, L2 is an important point. This is called a Lagrange point. There are a series of 5 points that were calculated by a French mathematician, Lagrange. And he said that these are 5 points where if you have 3 objects in orbit around each other, so here's the Webb and the Earth and the sun, if they're in orbit around one another, that this is the place where all the forces balance out and something can be stably put there and not fall one way or another. And so this L2 is the point they've chosen to put James Webb. And the main reason they've done that, and you can kind of see it in this picture here, is they're going to tilt it so that the backside of it is pointing toward the sun and the Earth, and the telescope itself is completely shielded from any light from the Earth and the moon and the sun. And the reason they do this, by the way, folks, is that the Earth and the moon and the sun are ginormous sources of infrared radiation. And if you want to put your eye out, you aim your telescope in that direction. So they want to make sure that James Webb never catches sight of Earth and the moon and the sun. And so you tilt it like this so it's away from them. And so this is what it looks like. So here's the Earth and the moon, and James Webb will be all the way here at L2. It's going to be executing this interesting and strange circular loop around this point as it goes around with Earth. And this loop is about approximately a 6-month loop that it executes going around. And the point of doing this is it's meant to keep Earth and the sun always on one side of it, so it never illuminates the telescope. But guess what? The moon is moving around the Earth like that. And so this goes in the loop over here to make sure that the moon never enters the field of view either. So James Webb has to do this circular motion like that to keep the moon and the Earth and the sun all out of its field of view. It needs to do this. So this is kind of an interesting and complicated kind of orbit, and but they very carefully calculated it, and it's going to ensure that the telescope is always pointing toward the part of the sky that is going to be really good to look at. And so here's what it looks like. The bottom side of Webb over here, this is the hot side that's facing the sun. It's going to get up to 185 Fahrenheit. The cold side facing away from it, it's down to -388, and that's very good. It's cold. You want your instruments to be very, very cold there. And then there's a communications antenna, so it can talk to Earth in the meantime, but it's always going to try and keep itself pointing away from the Earth. So here's just a few words on some of the science instruments. The bottom side of Webb, if you were to look underneath it, has a whole suite of cameras. There are cameras that take images, and then there are spectrographs that break the light into a spectrum. And then there's this neat thing called a coronagraph, which is kind of new. The coronagraph, it takes a little obstacle and it plops it down on a star that you want to look at, and it blocks the star out enough so you can see if there are planets around it. Think of it as being like if you want to look at fireflies and you have headlights of the car on, and you're looking into the headlight of a car and trying to see a firefly, you can't do it. You need to put your hand on the headlight so you can see the fireflies. Well, it's the same thing with coronagraphs. They block the star so you can see the light. And so inside of this this enclosure has these 4 instruments here. And you notice that virtually all of them have some spectroscopic capability and coronagraphic capability. And each one focuses on a different part of the infrared spectrum. And I believe in the coming lectures, the next 3 or 4 lectures, you're going to get a good intro from the experts on exactly how these instruments work, but they're pretty incredible. So what are some of the things that JW are going to study? So one of the most important things is to study redshifted light from distant galaxies. So here's Earth, and then here's James Webb, and here are these galaxies that are many billions of light years away. And because they are billions of light years away, these galaxies, the light we are seeing from them, it left them a long time ago. It left billions of years ago. And the universe, you may have heard, is expanding. Hubble discovered this years ago. And as the light from these galaxies is traveling through space, the wavelength gets stretched out longer and longer. And this is called cosmological redshift. So a galaxy that might be a few billion light years away, the light started out visible light. And by the time it gets to you and James Webb, it's stretched all the way out into the infrared. And so this is why, if you want to look at galaxies that are very far away, you can't use Hubble. The wavelengths are too stretched. It's beyond Hubble's capability to see. So you need a dedicated telescope like this one here that is going to observe in the infrared and really catch those really early on galaxies. So, and the incredible thing too is we're going to not only be able to see them, we're going to be able to have the best spatial resolution, and you have a huge mirror, so you have a lot of light gathering capability, and it's going to blow the socks off of anything we've done with early galaxies up till now. Things get even more interesting when you look at hunting for exoplanets. So here is an example of the kind of thing that James Webb will do in the infrared. This is what was done in the optical with Hubble. So here there was a star, and you can see these big spikes here, very bright star. And what they did was with this instrument that used to be on Hubble called NICMOS, they plopped a little aperture, a mask onto the star to block it out. And when they blocked it out, they were able to then analyze the light from that. And they were able to see that there are 3 planets here in orbit around the star like that. And it took a lot of massaging of the data to really get those to come out, but it shows you the power of blocking the main star like that. And another case where they did this was Beta Pictoris. So this was a star with a disk viewed on the side, and they blocked out the main star, and you can see that there's a disk of glowing gas and dust on either side of it where planets are residing like that. And so Hubble is going to be able to do this in the infrared. And that's the great thing about this, is that in the infrared, you can see things that are much cooler in temperature than these stars. And so we'll be able to see things that are behind a lot of gas clouds that Hubble can never see. So this is another incredible thing that you can do with James Webb. And then the final thing I'm going to mention here is James Webb can also do direct spectroscopy of planets. So here, this is a paper that was just published where someone from the ground on Earth looked, and this is an image that they took of a star and a planet orbiting it. And this planet, it turns out it's like a super Jupiter. It has like 10 times the mass of Jupiter, and it's orbiting almost 100 times farther away from the star than the Earth is orbiting the sun. So it's way, way out there. But they were able to take this and take a spectrum of it because it's so separated from the star. And here's the spectrum that you can see, and you can see these spectral signatures of water vapor and other molecules that might exist on a planet that you want to study. And what's amazing is, James Webb will have the angular resolution to analyze spectra of planets almost 100 times closer to their star than this one. So you're going to be able to see planets that are orbiting like here, like extremely close to the star, that Hubble could never, that the ground-based observatories could never reach. So you're going to do this in the infrared, and you can do it with higher resolution than anyone's ever done before. So it's pretty incredible. So here are my last few slides. I have a little video too that I can show. I'm just going to mention that, guess what? The launch of James Webb is just around the corner. So on December 18th, on an Ariane 5 rocket, it's supposed to get launched into space. So again, here's the Ariane 5, and here's the comparison what the mirror might look like. If you take this top of the Ariane 5, you can see James Webb folds up very neatly, like a toy, and even the main mirror has parts of it that fold back like that, and that gets put into a container. And in order for it to launch, it's supposed to launch from French Guiana. And so here's a little video. I'll just pause for a moment while you watch this. Here's the deployment of the telescope. Once it's up in space, it's going to start to unfurl the solar panels. And this is approximately, I believe it's 10 days after launch that this begins to happen. And then they have to separate the different layers. And these are meant to channel away heat from the far side of it encountered by the sun. And then we unfurl the main telescope itself and deploy the boom. And my last video here, it's a few minutes long, about 10 minutes or so, but it shows the late stage of deployment and there's some narration. And so I'm just going to leave it with that, and that'll wrap up our presentation. So,
Webb Telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of Earth and all eclipses. Additionally, the sun, Earth, and moon, the brightest objects in the sky, are hidden by the deployed sun shield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operations. Commissioning is completed about 160 days after launch, and the science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over the world can now use this facility to study the universe. NASA's James Webb Space Telescope is a game changer. Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into—
oh, okay. It seems to have cut out a little bit early there, but I think that gives the gist of exactly what we had. So, but thanks a lot for listening, and I'm ready to answer any questions that you may have.
That was amazing. Thank you so much. Go ahead and oh, you're not sharing anymore. Let me go ahead and put a spotlight on you because we love spotlights. Okay. Space is always so intimidating to me because it's big and vast and crazy, but you were able to really take some complicated things and make them where even I could understand them. So I appreciate that. Thank you so much. And I wonder what Galileo is thinking now. We're about to launch the Webb out into space. Do we have any questions? Let's go. You have an opportunity to speak with professionals. Let's see, Barbara, how many years will the Webb be operational? Do you have any idea on that?
It's interesting enough, I don't remember what the nominal lifetime of it's supposed to be. It's supposed to be a few years, but when you're way out there and far away from a lot of the things that might ruin a space telescope, it wouldn't surprise me if it lasts for like as long as Hubble did. I mean, Hubble's been going strong for 30 years. And I think Webb will probably go at least a couple decades.
I can help out with that as well. The nominal launched, the nominal mission duration is 5 years. And if we can conserve enough fuel on the spacecraft, we should be able to go up to 10.
That doesn't seem like enough time that we need. We need it to be out there longer looking at stuff.
Well, estimates are always very conservative. I mean, that's what they say about the Mars landers too. Like, yeah, we designed it to work for like 1 year, and then 10 years later, it's still going. They're well designed. They try to be conservative with lifetime just to, make sure that they are realistic.
Let's see.
Bronwyn, there was an earlier question from Robin O as well.
Okay. Oh, that's right. Thank you, Shireen. How does it maintain its orbit? Is there an engine?
Oh, that's a great question. I know that there's an engine that required to get it to go all the way out to the second Lagrange point. What I'm not clear on, and maybe Shireen can answer this, for it to go into that circular motion at the second Lagrange point, I mean, it's not orbiting any particular mass. I don't know if the engines continually fire to make it do that, or whether it has some more efficient way to do it. I don't know. Maybe Shireen knows.
There is a bit of propulsion on board that will fire an engine to maintain its orbit.
Well, and I hope that propellant is something that they very carefully calculated how much they have and need. So.
Let's see. Marjorie wants to know. But Beth has an. If James Webb observes in infrared, which we can't see, then how do we see it? Beth, that's a great question. And next week on Thursday, we're going to learn all about infrared and how the Webb is going to let us see that. But I will go ahead and let Parviz tickle us with that.
So infrared, you don't directly see with your eyes, but when it takes the infrared photons and records them onto a CCD camera or onto a detector like that, that then is translated into digital readout on a screen that then you see as visible light. So although you can't actually see directly the light coming from it, you can see though when it's been recorded, you can see what got recorded. It's kind of similar to an X-ray. Like when you take an X-ray of a hand, you can see what the X-ray penetrated through, but you can't actually see X-rays with your own eyes. And then the other question I saw here was that why did they launch from French Guiana instead of the US? And I think part of that is that the European Union had the Ariane 5 rocket that had the firepower needed to make it lift off. And they had a facility to do it. And believe it or not, NASA is still working to develop a heavy lift vehicle that could lift something like that. I don't think they're quite there yet, but the Ariane 5 has done this a bunch of times. And so that's my understanding. Maybe Shireen can correct me.
And also, Shireen might be able to say how long has it taken us to get to this point? And I want to add on. I mean, if it takes so long to get to this point, are we already talking about what's coming after James Webb? What's the next step in the telescope world?
Is this for Shireen?
It's for either board.
Why don't you go ahead?
Oh, well, I don't even know if we've thought much about what the next step is. There are other telescopes in conceptual design for other wavelength bands, like high energy, to go out into space. But right now, none of them are on this scale, and none of them are this far along in the development and ready for deployment. They're out there. One question I see here is who on Earth will be communicating with Webb? It turns out the communication is going to be happening right here from Maryland for the most part. They have a control center at the Space Telescope Science Institute. They've cleared out the 3rd floor in the main building there, and they've put the control center in there. So it's going to be happening, a lot of it from Baltimore and from Goddard, to my understanding. Along the same lines of the propulsion to maintain orbit, how will JW protect itself from potential space debris? That's a good question. Well, I guess they probably have calculated how likely it is to be hit by a micrometeoroid or a piece of space debris, and the space debris is much worse right around the Earth than it is out at L2. And although it's always like a bit of a concern, I think it's not going to spend much time near the Earth to have encounters with that kind of stuff. So, and then
the first images, I think, are, and what I've heard is 6 months it's going to take to get the first images. I don't know if y'all have heard something different than that.
Yeah, it's going to take, well, it takes a month for it to even get to where it needs to be. And then they have to go through this extensive period where they're commissioning the instrument. So they turn on everything, check to see if it works, calibrate it, make sure everything's okay. And then they start doing science operations. And that's going to take months to get to that point. So there's always that check-in phase. But if they see something, you know, really beautiful and they want to share it with the public, they're going to immediately do it. But in terms of like actual science results that people can publish and, you know, take to the bank, it's going to be a few months.
And what will a successful deployment be?
What constitutes?
Sam is expecting some failure.
Well, that's the thing. So I don't know how many backup systems there are, but they've thoroughly tested everything on the spacecraft. And of course, there's the unknown unknowns. You just don't, that could conceivably come up, but they've taken every precaution they can to mitigate all of that. And usually, I guess what I found is that whenever, like, at least with Hubble, when something breaks, they have enough ingenuity to figure out how to work around, and then they use like they have backup systems. And I don't know if JW has backup systems like the way Hubble does, but maybe Shireen can say whether they do.
I don't know the details, but there is some redundancy in a lot of the main systems. But I can't go into details. Hopefully some of our next speakers will be able to address that.
Yep, keep coming back because we're going in depth with the James Webb on all of these different aspects. This is our introduction. What is a telescope? What did we want it to do? What have it's gotten? How have we gotten to this point so far? So John wants to know if are we going to push a telescope farther out than L2?
Well, so I don't know that we're going to use other L points, because the other Lagrange points are at places that put you between the sun and the Earth. And if you're going to use an infrared instrument, it's no good. L2 is one place where you can have both the sun and the Earth on one side of the spacecraft at all times. So L2 is probably going to be the preferred place for the next few missions.
Are scientists still using refracting telescopes and finding good data with those, or is it just passé?
For the most part, there are amateur astronomers that are discovering like supernovae and asteroids and things like that use some of those. But for the most part, they've been supplanted with reflecting telescopes. So all the real meaty work gets done with reflecting telescopes now.
And I mean, I guess even with Hubble out there, it didn't supplant all of the work that's still being done. We're still getting good data from ground-based instruments.
Absolutely. And a lot of times Hubble works in tandem with that. Like the ground-based observatory will find some object and do a study, and then they'll say, wait, we need to see if this is 2 stars or 1 star. And then they propose for Hubble time, and then they can resolve it into 2 stars and study them. And so they work hand in hand all the time.
And is this a NASA program? Is it an international collaboration, or is it
James Webb? Definitely. Yeah, there's a whole suite of scientists from Europe and from some of the other countries too, not on the official government basis, but as people coming here to work on it that are lending expertise to this. It's a very multinational crowd. So
and Beth wants to know, can it go farther than L2? Everybody wants it to go farther.
Well, can it go far? Well, it could go farther than L2, but why would it want to? Because if it goes farther than L2, then the sum of the gravitational forces doesn't cancel out, and it'll fall back toward a lower orbit. And if it goes out, so that's an unstable point, that L2. You don't want to go farther out or further in, because then you can't maintain where you are. You want to sit somewhere in your orbit where you can always keep the sun and the Earth on one side, and having the Earth block the sun and the moon be blocked as well. So.
All right. Anybody? Oh, here we go. Many thanks. Many thanks.
There was a missed question earlier on.
Yes.
Someone
Okay.
wanted to know how long it took to, Marjorie wanted to know how long it took to develop the telescope.
A very long time. Actually, I think probably Shireen knows better than I do, but they've been thinking about this since Hubble went up. And they didn't kick it into full gear, I think, until like maybe the last, maybe around 2000 or so, because this telescope was supposed to have been launched. They were talking like 2010 or something originally. And then there were cost overruns, and then it got put on the shelf for a while, and then there were technical problems, and some of them were kind of embarrassing, and it's just a real complex thing. And so it's been a while, at least 2 decades, I would say.
And George is interested in who is James Webb and what did he get a telescope named after him?
Yeah, that's interestingly enough, it's become a source of a bit of controversy lately because people are talking about his background, but he was a NASA administrator around the time that JFK created NASA, and I think James Webb was the first administrator for NASA. And he was just a bureaucrat in the background there, and they decided to name the scope after him. As part of it had to do with preserving the project from cancellation. At one point I heard that they said, if you tack on the name of the NASA guy on it, it'll keep going. And, it kept going. But yeah, so he's I think the first NASA administrator.
Wow, named after a bureaucrat. There you go.
How do you like that?
Oh, Beth says he was little more than a bureaucrat in the background. So
yeah, he was a little more than a bureaucrat in the background, and look, he's got a telescope named after him.
That's your homework, everybody, before next Thursday. Learn more about who James Webb is.
Well, he was the bureaucrat at the right place at the right time. Yeah.
Right. Yeah, so I know that everybody is. I'm going to put in here in the chat box the link to the Padlet. Now that you know a little bit more about James Webb, or JW. If we're almost on a first name basis with it, you can send the telescope a love letter and see and add to our Padlet project here. So just copy and paste that link into your thing. And
we have one last question. We have one last question. What will happen to Hubble? The answer is that eventually Hubble cannot be serviced anymore because we don't have a shuttle fleet. And so eventually, one by one, all of its instruments will fail, and it'll just be a piece of junk up there. And so the plan had been that they would send a rocket up to attach to the Hubble and then cause it to deorbit, like it would fire its rocket so that Hubble's orbit would decay, and they would shove it into an uninhabited part of the Pacific Ocean, avoiding all population centers. That is what I told was what they were going to do. They don't want it falling on somebody's head, so that's bad publicity for NASA. So.
Wow, that's kind of, well, we all have to go somehow. But it's still up there. It's still doing great work, and it'll soon be joined by the Webb. And we all can't wait to see what it's going to see out there. We're going back in time, which is pretty amazing to see the beginnings of our universe. So thank you all for joining us this evening. You all look a lot smarter than you did when we started, so that's great. And thank you, Dr. Ghavamian, for sharing your time, your expertise, and your knowledge with us this evening. I do hope that everybody comes back as we continue our space journey, learning more about the James Webb Telescope and what we have learned and what we hope to be learning out in space. Stay well and stay curious, everybody.
Thank you. That was a great lecture. It was a lot of fun.
Thank you. Thank you, folks.